So this is our last talk before lunch. It's going to be a lab focus talk. It will be 20 minutes plus 5 minutes for questions. The group is Aaron Young's group from Georgia Tech. They were going to go after lunch, but Aaron's travel schedule means that he has to go now.
Can you hear me? Okay, great.
All right, take it away.
All right, thanks. So I'm Aaron Young. I'm going to be giving kind of a brief overview of the lab, and then each of my PhD students is going to give a kind of more specific research talk on each of their projects. So broadly, our primary goal as a lab is really to improve community ambulation with people with walking disability. And so we do this with a variety of different means, both prosthetic and exo devices. And specifically, we're looking at the role of power. So we add active actuation in both the exos and the prostheses and look at how that can help people in a range of different tasks that they might face in the community. And specifically, what we like to look at is the controller. So how does a controller adjust to provide variable walking speed, transition between different tasks, go up and down stairs, these types of things. And really looking at formal assessment of biomechanics and how the control affects human biomechanics in a range of different activities with a focus of really heavy human testing in the loop with these devices and real-time control. So I'm going to kind of give a brief overview of our control system, but first we'll kind of focus on what we're sensing. So what are the inputs to the control? So what's kind of traditional in the field is to just take a lot of different sensors from the robotic device itself. So these are mechanical sensors, could be IMUs, joint encoders, load cells, these types of things that we can embed in the robotic device. These are often very useful for control, but we also like to look at adding wearable sensors, so putting additional sensors on the human, and especially EMG sensors, so looking at muscle commands and how we can integrate these with control. And so one of the strategies we like to use is this idea of sensor fusion, of taking a ton of different information and letting machine learning type algorithms make the optimal use of this in order to try to understand what a person's trying to do. So our control system architecture that we use for our different devices is largely consists of 3 different kind of levels, the high, mid, and low level, and each student's kind of going to talk about some contributions within each of these. But to kind of introduce this concept, at the high level, this is really about estimating user state. So this is understanding what the person wants to do, what is their intent, like transitioning between different locomotion modes, for example, or what speed do they want to walk at, where are they at in the gait phase, or estimating ground slope. So different states of the user and the environment is really what comes out of this high-level control. And then at the mid-level, this is really dynamics equations that are in some way relating all of these different states to commanded joint torques in an exoskeleton or prosthetic device. And so these equations can be a lot of different types of models. So impedance control is pretty common, but others are admittance control or a torque controller that tries to mimic a biological torque, or even a kinematic controller. There's lots of different types of dynamics equations that can go in this, and we like to look at kind of what is the optimal human-machine interface controller at the mid-level. And then at the low level, this is maybe less interesting in some ways, but the idea here is your standard robotic control of trying to match a commanded torque with what the device is actually putting on the user. So basically tracking your torque or servoing a motor. Okay, so I'm going to introduce 2 projects. So the first of these is, so we have our own powered knee ankle device. We've seen a few of these already at this conference, but this is our version at Georgia Tech that we developed in collaboration with Aaron Ames. And so the idea here is we have 2 powered knee and ankle joints. We also have a frontal plane, inversion, eversion, passive degree of freedom in this device. And we've tested on a number of different amputees, and we have kind of 2 main goals right now with this project. One is to really understand how we can use the device to help offload the amount of work that amputees usually do on their sound side. We want to try to make the kinematics, or more specifically, actually the kinetics of movement to be symmetrical between the 2 sides with the robotic control, but also we're looking at user-independent intent recognition algorithms. So we really want to understand how to put on a device and let it automatically sync to the user and transition between different types of tasks. So we'll talk some results on that. The other robotic device that you'll see in the students' talks is this powered hip exoskeleton. So this basically provides active assistance in the sagittal plane for both flexion and extension. And the idea here is so what we've looked at to date is kind of human augmentation, so trying to understand how to control the device to reduce somebody's metabolic cost of walking. And we're looking to expand this into doing different types of activities, so stairs and ramps, and specifically how to enable community ambulation in a post-stroke population. So lastly, I want to introduce one of our new tools in the lab that we designed and built. So this is what we call the terrain park. And what's cool about this is basically we can modulate the stair height and the ramp incline angle with this large robot that sits under this platform. And it has embedded 6 COF force plates in it, so we can measure ground reaction forces. And then with full motion capture around it, we can really understand how exoskeleton and prosthetic users, in terms of their biomechanics, are responding to different controllers over a huge range of different conditions. So we're really trying to simulate community ambulation, but do it formally in the lab with biomechanics. And so next, so that kind of finishes my part, and now Jonathan's going to talk on some of our sensor fusion and machine learning techniques of the high-level controller.
Thank you, Aaron. Hello, I'm Jonathan. I'm studying PhD in robotics, and as Aaron mentioned, the high-level control is kind of the closest part to the user, and it must be aware of the intention of the user, and it should estimate the gait state. Then it should be able to elicit different changes in the mid-level control so that we can assist the user as it is intended. By using the terrain park, we are able to collect data from different sensors and study the biomechanics. And ultimately, our goal is to be able to, in real time, predict what is the user intentions and then provide that assistance correctly. Our approach, briefly, starts from the signal processing, where you collect signals from many different sensors, such as EMG or IMU, or the sensors that are embedded into the device. And from there, by combining that with feature extractions, you train your models to be able to do those predictions. The issue here is that once you start using so many sensors and combining so many features, it will be unfeasible to use your computational processing on the device to do these predictions in real time. And that's where sensor fusion is very important, and selecting what are the type of information that we want to use is very critical. In that sense, we analyze the signals and how they relate to the variables that we want to predict. And we do a smart feature selection where we find out what are the ones that produce a better prediction of the gait state. In that sense, we have found that methods as simple as one single layer neural network are able to use, by optimizing the features, are able to do the prediction of gait phase and also walking speed. And finally, to keep to reduce the noise and reduce the randomness of the output, we can use optimal filtering techniques such as Kalman filter. Using these, we are able to do real-time gait phase estimation, which is critical to provide the assistance in our devices in a timely manner. And we are able then to port this analysis into our devices. In this case, we are doing real-time estimation of gait phase for the hip exoskeleton, achieving user-independent gait prediction with an error close to 5%. We are also doing walking speed estimation. In this case, you can see how we are able to track the ramp of walking speed change for able-bodied subjects. And now I'm going to pass the microphone to Krishan, who is going to explain how we apply this on the power prosthesis.
Thanks, Jonathan. So I'm going to be focusing more on the high-level and mid-level control and how we implement this on the device. But first, I want to give kind of a little bit of a motivation. Humans have the natural ability to ambulate over different locomotion modes and different walking speeds. There's many current devices being made that can try to develop these more robust controllers. And really the focus, or one of the main goals of our lab, is how can we make our devices more adaptable to dynamic movements. So our powered prosthetic device is embedded with different sensors, which include 2 encoders, 2 IMUs, and 1 6-axis load cell. We're able to achieve high torques by modulating the torque via variable stiffness and damping coefficients through an impedance law that's paired with a finite state machine. So our experimental procedure for estimating continuous walking speed estimation is that we did a trial with 2 persons with transfemoral amputation at a range of 6 different walking speeds ranging from 0.63 meters per second to 1.7 meters per second. And I want to kind of go back to how we implement this into the device. And Aaron and Jonathan both talked about how we do sensor fusion and machine learning. So the first step that we do is that we pass in all these live signals into a signal processing regimen. So this is where we filter the data, this is where we normalize and we segment to the gate cycle. Next, we do a window selection and feature extraction. So I mentioned that we use a finite state machine to segment our gate cycle. And this is split into early stance, late stance, swing flexion, and swing extension. And what we do from there is we do this feature extraction on this window of 250 milliseconds. Next, what we're trying to do is we're trying to estimate this walking speed. So there's 2 typical methods that are used, either classification or regression. And we're focusing on regression because we want to do this in a continuous manner and not have our output have to distinguish between different classes. So the selected algorithms that we tried first was a simple linear regression. So it's easy, fast to use, and you can easily visualize it. The next one we did was a neural network. This kind of maps the input to the output by weighting different biases and weights. And lastly, we used a Gaussian process regression, which is kind of an in-between method. It's a nonlinear, non-parametric approach, but it still has the ability for you to kind of tune some hyperparameters and some kernel functions that fit the underlying data. So what I'm going to point to you on this graph right here is a comparison of all of these algorithms. So on the y-axis, you can see the root mean squared error, and on the x-axis, you can see the phases. Over all of the phases, you can see that the Gaussian process regression performed best. And the average error was about 0.04. And this really is the same thing as saying that you're only off by 0.05 meters per second. So we wanted to see how well this kind of generalized to other walking speeds over our training set. So what we did here is we did a remove one speed validation. So as you can see here, what we did is we took the speed and we excluded it into our testing set and trained on the rest. And what we get is from this graph is on the y-axis, we get the predicted speed and the actual speed. And we can see for a range of values in between, our algorithm is good at doing this interpolation, but at the edges, not so much for the extrapolation. And so what does this mean? So we want to be able to do this in terms of how we can take this continuous walking speed estimation and scale ankle power. We want to be able to use these methods for other things such as estimating ground slope or stair height. And lastly, we want to be able to make these robust controllers that can adapt to these dynamic movements. And now I'd like to pass it off to Inseung to talk about the hip exo.
All right, okay, thanks. Hi guys, my name is Inseung. So up to this point, so Aaron and Jonathan and Krishan kind of describe all the high-level and mid-level controllers and how we try to understand what user intends to do and what's the user state over a gate phase. But now I want to kind of bring back to a little bit more down to mid-level and low-level control layer where how the robot actually interacts with the user throughout the assistant levels. So So we see a lot of exoskeleton technology development over the years, and we've seen like full body exoskeleton, single joint actuated exoskeleton especially, but I want to focus on the targeting single joint, and we've seen a lot of positive results of achieving metabolic cost benefits with these ankle exoskeletons, which is phenomenal, but also the studies show that there is a major role for the hip joint as well during walking, which provides a mechanical power up to 45%. But the key difference between these ankle joint and the hip joint is that ankle joint is very efficient in using Achilles tendons, while the hip joint relies heavily on the pure muscle group, which kind of induces higher metabolic costs for walking. So with these, it's a very, I think, an exciting time to be in part of research and industry group trying to develop these different devices that try to achieve better energetic benefits. But the question is, what is and how should we assist better in terms of achieving the best results? What is an optimal assistance? To answer this question, our lab has built a bilateral hip exoskeleton using a set of series elastic actuators for allowing us to do a closed-loop torque control. This device has a power assistant around the sagittal plane for our flexion extension assistance with a 130-degree range of motion. It also has a passive joint at the frontal plane for abduction and adduction. One thing to know that what in our lab likes to kind of call it is a zero impedance mode, which basically is that you feed the commanded torque to be zero, which basically you're trying to zero out the interaction torque between the user and the device, so the user doesn't feel any impedance during walking with this device, which will be basically the baseline comparison for our study. So what is our controller strategy? We like to use this biological torque controller, which basically mimics the human biological torque profile, and we can change the different parameters relating to these, this controller over a gait cycle. We think that the three main factors that plays a critical role in these biological torque controller are the timing, duration, and magnitude. And with the timing, our previous study showed that by observing the metabolic cost benefits, about 45% of the gait cycle for the onset timing assistant for flexion, and 90% of the gait cycle for hip extension assistant will achieve the best metabolic cost results. And also, we did a small pilot study for the duration, so how long of an assistant we should give, and we observed this with the metabolic cost as well, and we found out that it's about 25% window length of the gait cycle that will achieve the highest metabolic cost benefits. So we set these two timing parameters, but the next question is, what about the magnitude? How much of an assistance should we give, and what is there a convergence, or is it linear increase? So with that, we set up an experimental protocol setting a null hypothesis that the increase of assistant will achieve better metabolic cost results. And we do a 3 different assistant level compare with a baseline of zero impedance mode throughout the gait cycle with using the onset timing and duration parameter that we found with, from the pilot work and the previous studies. So our experimental results shows that there is somewhat of a benefits of metabolic cost reductions with the increase of assistance, but we actually had a negative results with the highest assistant conditions. And to kind of understand what's going on over this with the upper bound of the assistant level, we looked over the kinematic data of during walking for the hip joint, and we kind of saw this, the increase of assistant, there was excessive hip flexions going on, which kind of induces certain like marching gait patterns. Also, one thing to note is that we were using the commercial off-the-shelf, the pelvic band, which kind of doesn't have a good interface, and we kind of observed this interface being one of the plays a critical role in providing a higher assistance. So one of the limitations of the biological torque controller is that it's not able to adapt to human body movement stride by stride basis. So you see that we preset the timing and the magnitude parameters, and it was basically assisting throughout the entire 6-minute walk trial. So we think that something like a biological signal, such as EMG signal, will be more versatile in providing assistance stride by stride basis. Another thing that we want to kind of look into is how does the control parameter interact with each other. You know, we see a lot of human-in-the-loop optimization. There's something that we're excited about. Lastly, we want to translate our technology into more real application, more dynamic locomotion using, like what Aaron said about terrain parks, for further future studies. These are our funding sources and collaborators, and I would like to take questions. Thank you.
Okay, we have a few minutes for questions. Looks like they're in the back. We'll get you the mic.
So I have a question to the mid and like low-level control part, the powered exoskeleton. So when you determine the onset timing and the duration of the torque profile, you determine it from the pilot's test, like determine the values which has the greatest effect on the reduction of metabolic cost. And I think the magnitude of the torque profile would affect the result and onset, would affect to determine the onset timing and duration. So what was the value of the torque magnitude when you determined those values?
So we kind of knew that the what magnitude we'll be using, like the conditions that we'll be using. So we used the middle one as like an average, and we tried that for the parameters. And that is one of the main limitations of biological torque controller, is that you have to fix the, you can't really see how the control parameter interacts with other parameters. Yep. And that, I do acknowledge that is one of the limitations, but we were just quickly trying to observe what are the window length that we wanted to use. So we just like a one subject quick test to see, oh, it's about 25% window.
So if you use different magnitude of the torque parameter?
Yes, that will definitely change. Okay. But we try to stay around within the range of what our experiments, our assistance is. Yeah.
Thank you.
This is a question about the exoskeleton right here. So you have a set timing profile and a set torque that you're giving assistance to, and then you said for the larger torques you saw this marching gait. Does that change based on, like if I walked in and I'm really lazy, right, and I'd put no effort in whatsoever, does that change the metabolic cost? Can this like basically carry me? And so my point is, depending on the person's acceptance of the device, does that change the result that you have?
So I think, and this maybe depends on the device as well, and I think the way that we're limiting the degree of freedom with our rigid exoskeleton kind of limits the user for more like versatile movements, and the way you give a high assistance will basically it works against you, where the device robot is not adapting to the user, but more like a user trying to adapt to minimize the discomfort. So we've seen that at the high assistance, we actually see that persons like try to move around their torso just to be just the exact amount of they want to get the assistance, I guess. And that's one of the, I think, the limitation of the torque controller.
I'll comment just briefly. So I think the two things. So first, regarding the sort of the person who's lazy, I guess. So this only provides kind of a percentage of what you have to do. So because you're on a treadmill, the person is forced. You can't just not do anything. You have to do a certain amount of work, and so. But what we do see though is there's a pretty big variability between people, and so you have people who respond a lot better to the exoskeleton and get big metabolic reductions, and others who just don't seem to know how to work with it, and they basically get no metabolic reduction. So what you don't see in this, I think there's 10 subjects here, but I mean, it's hard to say, something like half and half versus people who really respond, get it, and get a nice metabolic reduction, and those who don't.
Thanks for the awesome talk. My question is about the sensor fusion. Do you have an idea, like if you would rank what data is most important for high-level control, whether it's prosthesis data or muscle data or things like that?
Well, what we have developed is a way of finding out for each parameter that we want to assess what are the best features. So we apply the method for different cases. in the sense of gait phase, we have found that just joint joint values during the locomotion, for example, in the exoskeleton, are one of the most important features to use, and EMG also helps a lot during a stance phase. That's kind of our findings, but we are in the development phase of that process.
I have a hip exo question. Have you thought about including a ramp time parameter for your force control, for your torque control, since muscles will act with delays due to activation and contraction dynamics? Have you thought about you might be disrupting the muscle dynamics at the hip by having this sort of bang-bang control?
So we try to have a little bit of slope for this so it won't give a sudden impulse, but actually it doesn't make that much of a difference if you walk fast, because if your cadence or your step time gets faster, then you basically your gait phase gets like shrunk down, so you actually get an impulse. And I do agree, and we actually have there's a figure on my poster, but basically we did a comparison of the EMG proportional controller where you basically have a better system profile, and it was able to achieve better results with that compared to like having a more like a bang bang. Yeah, just like a sudden impulse. Yeah.
Thanks.
So I'm curious about something you just said about some people get a lot of benefit out of the exoskeletons and some people don't. And I'm wondering if you have any insight about what that might be like. Do you guys, who I'm sure wear the exoskeleton a lot, get more benefit from somebody than somebody that doesn't? And is it possible that you could you go in and give someone like really explicit instructions on, okay, here's how you use an exoskeleton and get better results than what I'm sure most experiments do, which is throw a skeleton on a bunch of random undergraduates and just sort of see what pops out of it?
Yeah, so it's funny because with other systems like upper limb pattern rec systems, you can train people and they get really good at using these type of things, and the people in the lab know how to do it really well. But with these exos, we find the opposite. In fact, there are people standing up here who are the worst exoskeleton users, and PIs as well, who are really non-responders. So we don't know how to train people. All we do right now is we put you in it for a couple hours before so basically there's 1 or 2 training sessions before they actually do the experiment. So they get quite a few hours of walking in it before you get it. But that doesn't make someone necessarily a great responder to it. And we don't yet know how to train someone to be a good. Well, we can look at the different people, but I guess what we don't know is, and certainly you have differences in their kinetics and what their strategy is, but trying to train someone to do it is not easy at this point. Yeah.
Are there other questions?
Cool.
Okay, let's thank them. A couple announcements. So right now we're going to break for lunch. We'll come